All right, class, so in this video, we're going to take a look at this naming binary ionic compounds worksheet. So this is an inquiry activity, and I'll just explain my thoughts as I go through the worksheet. So for this first section here, we're going to look at these 4 different compounds that we have and then answer the questions. So just taking a peek at what these compounds are, we have NaCl, which is sodium, and chlorine makes sodium chloride. Magnesium and bromine makes magnesium bromide. Potassium and chlorine makes potassium chloride. Calcium and iodine makes calcium iodide. So answering this first question here, does the first part of the chemical names for the above need to be changed from the original element's name? Let's take a peek at sodium chloride here. So we have Na, which is sodium, and in our name, we have sodium. How about this next one? Mg is magnesium, and over here, magnesium. And potassium and calcium. So this first question, no. This first part of the name does not need to be changed. Number 2, does the second part of the formula have to be changed, just like number 1? And if so, change to what? So for sodium chloride here, we have chlorine is the element. But instead of chlorine, we have chloride, ending in IDE. The second part, we have MgBr. Br is bromine. But instead of bromine, we have bromide. And if we look at these other examples, chloride and iodide. So yes, this does have to be changed. Yes, it is changed, and it's changed to IDE. Number 3, do you do anything with the number in the formulas when writing the compound's name? Well, let's take a look at our examples above. We have a number here on bromine, Br2. Do we see a 2 affect the name whatsoever? We do not. How about over here, the 2 on the iodine? There's no 2 anywhere in the name. So we know we don't have to do anything with the numbers in the formulas. So at this point, before we do number 4, you can go ahead and pause, try this on your own, and then check your answers as I go through them. So name the following, Na2O. So we know that we don't have to change the first part of the name. So Na is sodium. So we're going to write down sodium. And then we don't do anything with this 2. And then O is oxygen. But for the second part of the formula name, we have to change it to end in IDE. So sodium oxide. For part B here, the first part of the name is the first part of the compound is beryllium, Be, and we don't change that name. So beryllium. And the second part of the compound right here is fluorine. And there's a 2, we don't do anything with the 2. But fluorine, we have to change to end in IDE. So beryllium fluoride. All right, so that's the first section. Moving down to the second section right here. So in this part, we're looking at why we have numbers in certain compounds, but not in others. So we have lithium oxide, which is Li2O, strontium iodide, Sri2, and sodium nitride, Na3N. So where does the 2 come from in Li2O? Look at our periodic chart. So I'm going to pull out my periodic table over here. In our periodic table, I want to point out just a little bit of the organizational scheme of the periodic table. We have arrangements of groups of elements, and I'm saying groups very specifically because a group quite literally means a vertical column in our table. One very notable group that we have is the noble gases over here on the right. These are called noble gases because they don't really interact with anything else. We almost never find them in compounds in nature with any of the other elements. So because they are so highly unreactive, they have a charge of 0 almost always. Now for the rest of our columns, we can assign charges, for most of these columns, we can assign charges based off of what typically happens in nature. This has to do with the concept of valence electrons, which is something that we'll get more into later in the year. This first column over here, these elements, they actually want to gain 1 electron when they make a compound, or when they're on their own, before they make a compound. So when they gain 1 electron, they gain a negative charge. So they gain a minus charge. And it's a 1 minus, but we don't write the 1. This next group over, these elements want to gain 2 electrons. So they gain a charge of 2 minus. This next column, as you can see in our pattern, these want to gain 3 electrons, which is a charge of 3 minus. I'm going to pause here and go around to the other side. We can pretend like we have this left side of the periodic table and just put it on the right side right here. But we need to express it somewhere on paper, so that's where we've made our break. Because this first column here, when it is on its own, these elements want to lose an electron. So if you lose a negative charge, that means that you gain a positive charge. So these will actually be a 1 plus on our far left column. And again, we don't write the 1. This next column over, from beryllium down, these want to lose 2 electrons, which means that they will end up with a positive charge of 2 plus. All of these elements in blue here in the middle, these are called the transition elements. Now, the transition elements have a bunch of weird properties, and so they don't really follow our charge schematic. And we can get more into that later in the year, but we won't worry about that for now. So let's go ahead and skip on over to this group from boron down. This group, if we follow the same pattern from the left, this group wants to be 3 plus. So it will lose 3 electrons. Now this group in the middle, we have positives from the left and negatives from the right. This group actually wants to lose 4 electrons. So it will have a charge of 4 plus. And we can get more into this later, but this is where we get more into the realm of quantum physics and things like that. So we won't get too into the nitty-gritty details of that in this course. So these are our charges. If you haven't done so already, I very, very highly recommend finding a periodic table of your own and pulling it out here so you can either print it out and write down these notes, or have one on your computer that you can refer to that's virtual, but you can also make notes on. We will need to keep these notes as we go throughout the year. So make sure you pause and have a periodic table with these notes on it. So coming back over to our worksheet, the second section, where does the 2 come from in Li2O? So looking at our periodic table, lithium is over here in our 1 plus category. Oxygen is over here in our 2 minus category. In our compounds, we really want our compounds to be neutral. So that means that we need 2 lithiums with a single positive charge for every 1 oxygen with a 2 minus charge. So we have 2 lithiums for every 1 oxygen. That's where that number comes from. How about number 6? Why is there a 3 in the formula for sodium nitride? Well, this is for a very similar reason. So sodium is over here in our 1 plus category, and nitrogen is in our 3 minus column. So we need 3 sodiums to balance out the charge of 1 nitrogen. So that's why we have 3 sodiums for every 1 nitrogen. You can go ahead and pause and try number 7 on your own before I give the answers. So write the formulas for the following, and don't forget they might contain numbers. So potassium selenide. So the first thing I'm going to do is I'm going to write potassium and selenium and leave some space between because we don't know the numbers yet. Potassium over here is in the 1 plus category. Selenium is in the 2 minus column. So we need 2 potassiums to balance out the charge of 1 selenium. So we need 2 potassiums for every 1 selenium. Moving on to calcium chloride, I'll start with the same process. I'll just write calcium and chlorine, leaving enough space in case I need to write numbers in either spot. Calcium here is in our group of 2 plus, and chlorine is in our group of 1 minus. So we need 2 chlorine atoms to balance out the charge of 1 calcium atom. So 2 chlorine atoms for 1 calcium, and we won't write the 1 here. But there we go, that's where the numbers come from. All right, this next section takes us back to these polyatomic ions that we've learned about this past week. So number 8, what's going on with the groups of nonmetals like NO3? What are they called? NO3 minus, excuse me, I'm going to make sure I say that. So these are our polyatomic ions. Why do there have to be parentheses around groups like this nitrite here, the NO2? with a 2 afterwards. These parentheses, if we look at balancing the charges, let's look at this calcium nitrite. Calcium, if we look at our periodic table, is over here in our 2+ category. So calcium is a 2+, and nitrite, if you remember from our polyatomic ions, nitrite is a 1-, so we just write a minus. So that means we need 2 nitrites for every 1 calcium. So we put the parentheses around our nitrite to make sure that we contain nitrite as a unit. So as a unit, we need 2 nitrites for every 1 calcium. So you can go ahead and pause and try these answers before I go through them. So name or write the following, or the formula for the following. Cesium permanganate. I'm going to write the formula for permanganate over here on the right side, just the polyatomic ion. So we have MnO4-. So this is a -1. And cesium, if we look, is in our 1+ category. So for every 1 atom of cesium, we need 1 polyatomic ion of permanganate. That makes it nice and easy. CsMnO4. Done. Ammonium oxide. In this case, ammonium is our polyatomic ion, which is NH4+. Now oxygen, let's look at where this falls on the table. It's in our 2- column. So if our ammonium is 1+ and our oxygen is 2-, we need 2 ammoniums for every 1 oxygen. So since we need 2 ammoniums, we want to put parentheses around NH4 because we need to contain that as a unit. 2 ammoniums for every 1 oxygen. Beryllium phosphate. Now phosphate is our unit here, and phosphate, the formula is PO4-3-. Beryllium, let's look at where this falls on the table. It's in our 2+ column over here. So we have a 2+ for our beryllium and a 3- for our phosphate. In order to find a neutral compound, we need to have these charges balance. We can't just multiply one of these by a certain number because 2 goes to 4, which skips right over 3, and 3 is already more charges than 2. So what we have to do is we find the least common multiple of the charges of these ions. So 2+ is the charge here, and 3- is the charge here. So the least common multiple of 2 and 3 is 6. So we need there to be 6 positive charges and 6 negative charges. For beryllium, to have 6 positive charges, we need to have 3 berylliums at our +2 charge, at our 2+ charge, excuse me. For the phosphate, to have 6 negative charges, we need to have 2 phosphate ions. So remember, we contain this as a group, as a whole unit, PO4-2. And there's our compound. Great, so moving on to the last section here, I'll pull over the next page. So this section is on hydrates. So let's look at our examples here. We have CaCO3.2H2O, calcium carbonate dihydrate. Second example, we have CSF.5H2O, cesium fluoride pentahydrate. So let's look at these questions here. 11. Did the addition of .2H2O in the first example do anything with the name? Well, our name here, let's take a peek at just this first section, CaCO3. So we have calcium, and then this is a carbonate polyatomic ion. So calcium carbonate, that's exactly what we'd expect. But in our name, when we add .2H2O, the name adds dihydrate. So we're going to come down to these prefixes down here to really understand where that part of the name comes from. This dot means loosely bonded to. That means that we don't include it in the same chemical formula like CaCO3. These are strongly bonded. This dot means loosely bonded, which is essentially like they just hang out together. The 2H2O, if we come down to these prefixes, 2, we have di, and H2O, we call a hydrate unit. Like if you're drinking water, you're hydrating yourself. So we have 2 hydrates, which is why we call it a dihydrate. Let's take a peek at the second example as well. So CSF, this is cesium, and this is fluorine. If we remember to the first section, we don't change the first part of the name, cesium, which is cesium, And fluorine, we change to IDE, fluoride. That's what we'd expect. Now we have dot, or loosely bonded to, 5 H2Os, which 5, the prefix for 5 is penta, and H2Os is a hydrate unit. So we have 5 hydrates, or pentahydrate. There's our pentahydrate. Number 12, what do the names of these two compounds have in common? What's different? So I kind of already went over this, but this first part, calcium carbonate, is what we'd expect, calcium carbonate. Cesium fluoride is exactly what we'd expect, cesium fluoride. And then they both end in something hydrate, something hydrate. That's what's similar. What's different is the number or the prefix in front of the hydrate. And we come back again to this number that's in front of that hydrate. So now you can go ahead and pause before I give the answers to number 13. Try it on your own. So for number 13, part A, name or write the formula for the following: MgSO4.3H2Os. So that means we have magnesium, which we don't change that name because it's the first part. Magnesium sulfate is SO4, and that's a polyatomic ion, so we just leave that name as is. And then dot, or loosely bonded to, 3 waters. So 3, the prefix for that is tri, and then we always say hydrate. So trihydrate. If I get my my capitalization correct here. Trihydrate. For part B, lithium carbonate monohydrate. So lithium has a charge of 1+ on our periodic table. Carbonate, I'm going to write this right above here. Carbonate is CO3 with a charge of 2-. So to balance out 1+ and 2-, we need 2 lithiums for every 1 carbonate. So Li2CO3, lithium carbonate. Then monohydrate means loosely bonded to, or dot. Mono is the prefix for 1, and hydrate is H2O. And again, in chemistry, we don't really write our 1s. So these prefixes are vitally important for you to understand and remember. Memorize these, memorize these, memorize these. If you need any help, it's very similar to geometry. If you are thinking about just how many different sides a shape will have. So we have 1- and 2-sided shapes don't really exist, but triangles. Technically, a shape with 4 sides is called a tetrahedron. And we have pentagons, hexagons, heptagons, octagons, nonagons, and decagons. So it's the exact same prefixes for geometry are what we use for these hydrates. So make sure you memorize those, and make sure you bring your periodic table with all of your notes. But that'll do it for naming binary ionic compounds.